Okay, so how do we work out the pressure in the middle of a star? I should warn you that this video we're going to be using some rather more advanced maths than we've used elsewhere in the series of courses, in particular calculus and integration. If you don't feel up to this, feel free to skip over this video and just go on to the next one. But if you're up for a challenge, let's go. So let's imagine we have a star, the sun or a white dwarf or something, and it's got a pressure in the middle. How can we work that out? Well, all the outer parts of the star are being sucked by the immense gravity of the star towards the middle. Why don't they collapse in towards the middle? Well, there must be some force pushing out to hold them where they are. And that force is caused by a pressure gradient. What it means is the pressure in the middle must be bigger than the pressure out here. So let's zoom in. Let's have the surface of the star, and let's take a cylinder of gas somewhere in the interior of the star. Now it's got an area A on the top and bottom, and a thickness which is quite small, so we'll call it delta R, that being the calculus notation for a small amount of radius. And this cylinder is going to have a mass. The mass of the cylinder is going to be its volume, which is A area times the thickness, delta R, times the density, rho. We're going to assume unrealistically that the density is constant throughout the star for this calculation. In reality, of course, density increases towards the middle, but this approximation will get us a rough answer. So we've got that. That's the mass. So there's going to be a downward force due to gravity acting on that mass. How much is the gravity? Well, there's a clever trick. You may remember in a previous course we did this in respect to dark matter. We can divide the star into two bits. We can divide into all the bit that's further down than the cylinder and all the bits that are further up. And it turns out that the net gravitational effect of all the bits that are further up cancels out. There's no effect, and we can treat everything below it as if it were a point in the center with the same mass. So what's the mass of everything down here? We'll call that mr, the mass of everything up to radius r in the star. This is the radius r. And mr is going to be the volume below that, which is the volume of a sphere, which is 4/3 pi r cubed, times the density. So that's the mass, and that mass acting from here will apply a gravitational force downwards. So that force is going to be given by Newton's law of gravity, G mr, this mass here of this little cylinder, over r squared. Okay, so we've got a gravitational force pulling downwards, but in steady state that level of the gas doesn't shrink down. It might do that in the middle of a supernova explosion, but normally it's just sitting there. So there must be some equal and opposite force pushing it up. And what's that force? Well, the pressure here must be a little bit more than the pressure up there. What is pressure? Pressure is just all the molecules zooming around and banging into surfaces. So there must be more molecules, or they're moving faster, which means a bit hotter at the bottom. So as they all bounce off here, and a bit less bouncing off there. So there's going to be a pressure gradient. So there's going to be a delta P, a change in pressure from the bottom to the top, and that applies an upward force to balance out the gravitational force. So let's balance those things out. The pressure force is going to be pressure is the force per unit area, so the total force unit pressure is going to be the area times delta P. So it's area times P at the bottom minus area times P at the top. That's being the change in pressure. There's going to be no sideways pressure because the effects on all sides will be equal and opposite. So it's only the difference from the top to the bottom that matters. So that's the pressure force, and that equals G mr m over r squared from over here. Now, we know what mr is. So we can substitute that in and get G over R squared times 4/3 pi R cubed times the density. That's mR. Now what's this m here? That's given up here. So that's A delta R rho. So what we can see is that we have an area on both sides that cancels out. So we've got the pressure difference in pressure and the difference in radius here. So we've got two small changes. We take the ratio, that's what you do in calculus. So you get dP by dr, and that comes out as 4/3 pi. We've got R cubed over R squared, so it just comes out as R G times the density squared. We have to be a bit careful about the sign here. This is how much the pressure increases at the bottom. If you're measuring how much the pressure decreases, there'd be a minus sign here. It all depends which way you define things, but let's leave it as that for the moment. So that's given us the pressure gradient. This is a small change in pressure over a small change in radius. What we can do in true calculus fashion is take that to the limit, so make them both go small but preserve the ratio, so that's dP by dr.